and thank you for coming back. So we're going to continue day 3 of the proof of the shuffle conjecture. So last time, just as a reminder where we left off, we were basically trying to prove this theorem right here, right? We had just introduced a bunch of operators, right? So we had these raising and lowering operators, and we basically were trying to translate this whole story, all this combinatorial story, to the language of these new operators, d plus, d minus, ti, ti inverse, etc., on these bigger spaces vk, which are basically just symmetric functions tensored with some extra variables y1 through yk, right? And so we define these operators, ti, ti inverse, which are just basically de Mesure-Lustig operators. We define these operators d plus and d minus, which are basically compositions of the de Mesure-Lustig operators with a plethism. And then the d minus was defined similarly by taking a plethism and then composing it with this plethistic exponential, right? Which is just a sum, a series of hn, right? And okay, great. So, and then the big theorem that we were trying to prove here was that if you can generate the symmetric functions that arise in the formula for in the shuffle conjecture, right? These chi pi zeros and chi pi ones, that we can generate them for any dict path just using these operators d plus and d minus, right? And the gist of this theorem is basically, if you give me a dict path, you know, we're doing A1 north steps, then B1 east steps, and so on, then chi pi 1 is literally just equal to the symmetric function that you get by starting at 1 and applying the operators in this order, right? Where every time you see a north step, you substitute it for a d minus, and every time you see an east step, you substitute it for a d plus. So this is where we left off. And then as a corollary to this theorem, we want to show that if instead of replacing this directly, if instead every time we see a corner, right, like for example in this example, or in this dict path here, every time we see a corner, if we substitute that corner for this quantity here, which I called phi, just because it was easier to write in the example, which is basically just a scaled version of the commutator. If you substitute every corner for a commutator, but then leave every other north or east step assigned as you did in the theorem, then you actually get chi pi 0, which is the one that actually shows up in the shuffle conjecture, right? Okay.
Can I comment? So,
yes.
So just about this theorem. So if it's not, so why dict paths are important? Because if it's not a dict path, you get 0, right? Because you start composing this thing. You start from V0, you go up, and then you go down, and then you go up and down. So the dict path condition means that you never go below V0.
Exactly. So somehow,
if you have an element of V0 and you apply d minus, you get nothing. You get 0. And so dict path condition ensures that you get an interesting non-zero element.
Exactly, right? Because just to iterate what Eugene just said, if you're starting, for example, here, if this is 1 in V0, then the D plus bumps you up to D or to VBL, right? Because you do it, D plus bumps you up one level in the VKs, and then the D minuses bump you down. So if you're already at V0 and you do a D minus, there's no V minus 1, right? So the fact that you have more D minuses at any given point than D pluses, or at least equal as many, that ensures that you're never below the V0 level, which is equivalent to saying you're never below the dict path condition. So that's what he's getting at. Thanks, Eugene. It's a good point. Okay, so then our goal was basically to prove this. And the way we're gonna prove it, right, reduced to basically showing that these symmetric functions that we defined, these chi primes, which were almost the same things that we had before, right? The same thing as these chi's, except we're indexing over a different set, right? We're not indexing over any word. We're indexing over words that satisfy these conditions, this u pi sigma. Then using these, we wanted to show basically that if we take these and then we plethistically modify them, then the proof reduces to showing that if we basically inside our dict path, if we act by an e step, that translates to acting on these symmetric functions by a d plus. And likewise, a d minus translates to acting by a north step, right? So this is kind of the goal of what we wanted to prove. And in order to prove it, we had this handy dandy proposition, and this is the last thing we did at the end, which was basically telling you how these chi's behave when you're just acting by a simple transposition, right? So this is SM is a simple transposition, and it's basically telling you if you have sigma, whatever you want it to be, and you have a simple transposition, then that translates to acting by Q, and then a TM inverse, right? Where T is this Demeter-Lustig operator that we just talked about. So this was the end, and what we're going to do now is prove this goal, right? So first claim, we want to show that chi of k plus 1 of e pi is the same as applying d plus. So east corresponds to applying a d plus. How do we do this? So this is kind of, I rewrote this, like I said, or I pre-wrote it, so we're going a little bit faster. What do we need to do? So the first thing is we want to set our pi to be in dkn, right? And so then that means that taking an e step is just basically in this set, okay? And our first goal is to express this function here, this chi k plus 1 e pi, in terms of the smaller one, even if we don't have a d plus yet. Let's just try to express it in terms of it. So how are we going to do that? Well, we're going to set sigma to be this very specific composition or series here, right? K plus 1, 1, 2, all the way to k. And then if we see sigma just basically a standard ordering from 1 to k, we're going to say that it's the identity. So if you ever, instead of a sigma, see an identity, that's what that means.
Could you zoom in a little bit?
Oh yeah, sorry. Here, actually, let me. That's better, yeah? Excellent. Okay. So like I was saying, we want, so we have sigma and sigma prime. And then the claim is that there's a bijection between these sets U, right, that we had defined before. So just as a reminder, I have it right here in blue, what that U was. So there's a bijection between U, where we set the sigma equal to just this identity, kind of identity permutation, if you want to think of it that way, to U, where instead of pi, we have pi composed or pre-composed with an E step, and then this sigma that we had set here before. And what you're doing is at the level of words, we're sending this word to this word, right? So we're basically just inserting a k plus 1 right in front. And aside from that, it's the exact same thing. Okay, so that's a bijection. I'm not going to prove it for you, but you can go through and check it. And it's basically not very hard to see. And so then we have a couple of observations based on that claim. First observation is that if you look at the inv of e pi, right, words on this side, e pi with this word in this dict path, it's the same as inv on this side, but plus k. So that's the first observation. And then the second step is the following. So if we take our chi prime sigma pi, right, the symmetric function we had defined before, and here I'm going to label my variables by zi for technical reasons that will prove useful later. So if we just take our symmetric function here, then if you just go through and run it, and substitute the pi for the e pi, you substitute the individual pieces. So if you just compute this, right, this is equal to this. Why? Well, if you just ignore this line for a second and move to the blue, then this is equal to this, right? All I'm doing is I'm basically in this formula substituting pi for e pi, pi for e pi, w for f of w, w for f of w, and then now I'm summing not over my set here, but I'm using my bijection to sum over words here, right? So it's basically just transplanting or substituting everything in this formula for what it should be. Then this becomes this equation because the inv is just this plus k, right? Did I lose a K? Yeah, I probably lost a K here. Sorry, I just realized I probably lost a K. Let me fix that. This should be like Q to the K, hang out here. Right, because we're getting Q to the N plus Q to the K. And then Z to F of W, well, if you look at the words, this word and this word are exactly the same, except you have a K plus 1, right? And that K plus 1 is exactly why you're getting this showing up here. So you have an extra variable, which means that this is really just that. When you take the K out of the equation and you take the ZK out of the equation. So that relates our chi prime to chi prime with this particular sigma, right? Not sigma, not this sigma anymore, but this sigma. Okay, so, right, we have a formula, that's great. So here is where the yi and the x's come back into play and why we had all these z's showing up. So we're going to replace, third step, we're going to replace in this equation here, right, we're going to replace on this side the variables zi for yi when I is smaller than k, and then we're going to replace the variable zi with xi minus k for I bigger than k. So that's on this side. And then for this equation, for this side, we're going to do the exact same thing, except, oh, this should be e pi here. We're going to do the exact same thing, except instead of cutting off at k, we're going to cut off at k plus 1, right? But same idea. So we're substituting variables here and here, zi's for yi's and zi's for xi's, basically, depending on k or k plus 1. And that's
Can I make a comment observation just to check that I'm on track?
Absolutely.
Which is, so when we put in an honest dict path, we'll get something symmetric. But when you do e pi, that's not a dict path anymore. And that's why what we get isn't symmetric. We have the zk plus 1.
Exactly. Yeah, that's a great observation. Thanks, Monica. Yeah, if I am going too fast, slow me down. Like, there is a lot to cover, but the goal here is to learn. So I just, don't let me get away with just like speeding through everything. I have read this many times, so I'm not the target audience here. Okay, so then what does that tell us? That means that if we, in this equation, we make this substitution, then we get the following equation. We get that the left-hand side, I want to have everything on the screen here. Okay, this side, well, that's just here, whatever. We just substitute the appropriate variables. But then here, we get this equation, right? Because essentially you get a plethism by changing these variables around. And then if we recall that we could get the unprimed symmetric functions from the primed symmetric functions, then that means that if you just substitute everything through, right, and you make the notational change where if you have a one, like the identity permutation here, the identity word here, and you just write that as k, then you end up with the following expression, right? And this is just basically a direct computation of using this equation here and using this equation here, and then you get this. There's nothing enlightening there. But why is that cool? Because it gives us exactly what we were after. It gives us a way to relate this chi sigma in terms of this chi where you're just working by the identity. Okay, now one more step. So now we're going to use that proposition that we mentioned. So we're going to observe, first of all, that the permutation or the word or composition, whatever you want to call that sigma, can be obtained from basically doing nothing, just the identity, by swapping, by simple transpositions, right? Just by swapping consecutive entries. And then we're going to recall our proposition that told us that if we see a sigma and we apply a simple transposition to it, we get something of this form, right? That's what that proposition said. There are some conditions here on the sigmas, but they're satisfied by our choice of sigmas and sigma and identities and whatever else. So the point is this holds. Okay, and so what that means is that if we go back to the equation here and we just do it to the left-hand side, right? Then we can rewrite that sigma, which was this, by just iteratively applying this as this, right? So it's just basically you apply this once and you get you move the k over to the 1, and then you apply it twice and 3 times and so on, k times until you move the k plus 1 all the way to the right-hand side. So this k plus 1 here, right, this is just saying like 1, 2, k plus 1. Great. And then from here to here, all I did is I moved all this stuff to the other side, which gives me this expression. And now we put things together. So we remember that this chi sigma e pi by this equation here, right, by step 4, this can be written as a plethistic modification of chi k. So we're going to take that and basically just plug it in instead of this, which is how we get this. This qk cancels with that q minus k, and we just get this expression, right? So we're just altering this side. And then we just notice that if we go back to the definition of D plus, this is exactly what D plus is. D plus is you apply a bunch of TIs and you plethistically modify. So it just falls out of the definition, which I think is pretty neat because it's just literally a computation. There's nothing super cool happening here. It's just clever. Yeah. So again, any questions, stop me. But yeah, it's very, very straightforward. And then I'm not going to do the proof for this because, again, it's kind of the same idea where you just go through and follow your nose and play around with the formulas. But you can similarly prove that basically if you do a north step, it translates to applying a D minus. Yeah, so that proves this theorem that you can get chi of pi 1 by basically just applying a bunch of D pluses and D minuses indexed by your dict path, right? Which is pretty awesome. What else? So now, how do you prove the corollary? So the corollary, if you remember, we had this formula that allowed us to relate, to decompose any given weight into a sum of other two pieces, right? And that basically allowed us to write chi of pi 0 as a sum over chi of pi 1s, right? We did an example for this. And basically, if you just use that exact same procedure, you can derive that from this theorem, because this was with weight 1, from this theorem, applying this formula iteratively, you can derive that if you just substitute every corner with this commutation relation, then you get chi of pi 0. I'm not doing it, but it's basically, you can just go through and check it. Yeah, any questions about the proof or the, yeah, anything? I feel like I had too much coffee, so I'm like shaking a little bit, so I'm sorry. I think I've been up since 6 and I might be speaking really, really quickly.
I have a general question,
Yes.
not about this, but we just discussed it with Monica over chat. So I think, I don't know. And is there any relation between this chi of pi 0 and chi of pi 1 with Catalan functions that we discuss on Mondays? And like from this work of Morse, Basic, and other things, other people. So I think the answer is yes. I don't know any precise relation. And I think like Eric at some point said, yes, of course. But I'm not sure. And I think this is like a good general question how to relate the two. So you have like two families of symmetric functions labeled by dict path, right?
Yeah.
And yeah, just want to put this question out there. And
That's yeah, I don't know.
or
yeah,
we should all go and ask
what do you
Eric.
think about it? That's a really good question. I like it. Yeah.
Maybe we should just Eric on Monday. Yeah.
Yeah, we can talk about it in the exercise session after this. Also.
Yeah. So also the Catalan ones, they were sure positive, is that right? And I don't know about, I mean, I haven't looked at, I mean, you know, this, I haven't seen any of these pi's decomposed into Schur functions, for instance, and seen what the expansions look like. I don't have a sense of them on that level.
These should be Schur positive, I'm pretty sure. I mean, it's again the same LLT argument that like you can write them as sum of LLTs, and LLTs are Schur positive abstractly.
Yeah, but I mean, if we knew how to divide chi of pi 0 into Schurs, we would have like nabla of Vn into Schurs, which last time I checked isn't known, right? So I mean,
yeah, but
great.
like,
That's a good question, obviously.
but like chi of pi 0 is like the contribution of one dict path to shuffle conjecture eventually, right?
Mm-hmm.
So like it's sum over all Parkin function support on this guy. Yeah.
Ah, yeah. Okay.
This is a great question. Thanks, Eugene. You should definitely bring it up again because, yeah. Okay, so now what are we going to do? Now we're going to move past those theorems, which we will use later. And what we want, right, is to go back to the goal of expressing d alpha qt, which, let me remind you, we had, right, the statement of the shuffle conjecture was precisely that, or the compositional shuffle conjecture, was that Nabolev C alpha, sorry, was the sum over like t to the bounds of pi times chi of pi 0, right? And this right-hand side is what we were calling d alpha of qt, just so that we're all on the same page. So the goal of the theorem, right, or the goal of the paper is proving that this left-hand side is equal to the d alpha qt. So what we want to do is basically we have this internal part, right? We have chi of pi 0. We just expressed that in terms of these operators. So now let's take it further and express d alpha, which is the sum over all these things in terms of these operators. That's the next goal. Okay, how do we do it? So we're gonna introduce more operators, right? And so we're gonna say, all right, let's suppose alpha is any composition of length L, and we're gonna define n alpha to be a function, or yeah, in VL, where L is the length of alpha, right? We're going to define it recursively in the following way. So we're going to set n of the empty composition to be 1. We're going to set n of basically taking our composition alpha and appending a 1 at the beginning. Then we're going to call that 1 alpha. We're going to define that to be basically n alpha precomposed with d plus. And then we're going to do the same thing here, where instead of appending a 1, we're going to append an a. Here, a has to be bigger than 1. So let me just say a has to be bigger than 1. And then that is going to be basically given recursively. This is where the recursion is coming in terms of different paths, beta, that are compositions of size, or sorry, compositions of a minus 1. Right, and then you just apply this formula. And then the big theorem, right, is that this d alpha can be obtained from these recursively defined functions by just applying d minus of L, right? And this d minus of L is basically saying, remember that d alpha qt is supposed to be a symmetric function. If it's a symmetric function, it has to live on V0. So these n alphas are basically created by these d pluses. You start with 0, you start with 1 in V0, you go up to VL, you do all these computations, and then you bring it back down. And to bring it back down, you're applying this d minus L times, right? So that ensures that this is basically just living in V0. And so that's the theorem. So let's do an example, because I find these operators by the definition a little bit confusing. So let's just do an example for alpha equals 3, 1 to see how they would be, how you would use them. So step 1, n of the empty set is 1. Good. Now we're going to do n of 1. So 1 of the empty set is just basically you apply d plus to n of the empty, right? That's what this is saying. If you have 1 of alpha, you apply d alpha to n of alpha. So here we're just saying let alpha be the empty set. So that's d plus of 1, 1. Good, because d plus of 1 is always 1. D plus of any power is of 1 is always 1.
It's a different one though, right?
Yeah. That's a good point. So it's a different one. Yes. So this is a 1 in V0, right? You have to keep track of the level that you're in. This D1, so this was in V0 and this is now in V1 because D plus bumps you up to the next level. Good. So how do we do 3, 1? So 3, 1, we want to use this formula. So here we want the alpha to be 1 now, and then the a to be 3. So we just apply it, right? So this is this, then the commutator. And so then we want to sum over all compositions beta such that beta is equal to, or sorry, such that beta is a composition of 2. So basically you have 2 and then you have 1, 1, and that's it. And then, alpha should be 1. This is 1. Okay, And so then how did I get this? Well, basically I just did it individual. I said, all right, beta could be 1, 1, right? So then it'd be 1, 1, 1. That's n of 1, 1, 1. And then again, you just apply the recursion. N of 1, 1, 1 is d plus of n1, 1. It's d plus of n1 and so on. And you basically just apply d plus 3 times to get 1, 1, 1. And then n of 1, 2, which is what you would get if you substituted beta for 2. So prepending a 1, right? Again, we go back to, if you're putting a 1 at the beginning is adding a d plus. So that is d plus of n2. And then for n2, we want to think of this as a equaling 2 and alpha equals 0, right? And then we play the same game again, but now we've cut it down to betas of size 1, which is just obviously the one thing. So if we just go through and work it out, right, this is just going to be one term, which is when alpha equals 0. So let me, alpha equals 0, and then beta has to equal 1, which is n of 1. The length of beta is 1, so 1 minus 1, which is why I have a 1 minus 1 here. And then you work it through. And then basically at the end, what that means is that you take n31 and you just plug it in, right? So we get this is equal to d plus plus substituted in here, and then this stuff substituted in here. So if you just, this is just putting all back together. And if you were to actually do it by hand or through a computer, you would see that this gives you this, this function, right? Yeah, and it's living in
Right.
Yes.
So d plus of 1 is 1,
Yes.
but d minus of 1 is something interesting, right?
D minus of 1 is not necessarily 1. Yes, it's
Yeah.
yeah. It's 0 if you're in V0, right? So this is why.
Yeah.
But yeah, exactly.
So here, these two terms, can you say that these are chi of pi 0 for 2 digpass?
That's exactly what it is. Yeah, that's exactly what it is, right? Because essentially, I mean, that's exactly how you're getting this equality at the end, is that this is supposed to be, you know, the sum over t to the bounds over some dikpats, right, of chi of pi 0. So necessarily you're going to get that this part and this part correspond to chi of pi 0 for 2 different dikpats, and they're the dikpats that you would get.
Yeah, I mean, sorry, I'm just asking about this form, the previous formula actually. So the previous formula, you have this commutators of d minus d plus, and like from your previous theorem for chi pi 0, you were saying that these are corners of some things. So like
Yeah. But that's the whole point. That's exactly the whole point. If you actually trace the shape, yeah, if you trace the shape, if you think of the first summon as being like d minus, d plus, and then a commutator d minus, d plus, d plus, this is going to give you something, right, where you had like a corner. Maybe I did my corner backwards. So d minus, d plus, or is it d plus, d minus? Let me get the signs right. Anyway, sorry. Let me go back here. Yeah, so this should correspond to something like a corner, and then you did an E step, and then you did another corner.
Might be too big, but okay, let's see. Oh no, 1, 2, 3, 4, 5, 6. Okay, never mind. Yeah.
Something like this, and maybe the path is backwards. Potentially the path is backwards. And then this the bottom thing would be the exact same thing, right? You had a corner, and then you did a north step, and then you did 3 east steps. And these dikpats are potentially backwards. And I bet you that if you go through and write the dikpats in the right, starting and ending at the right place, because again, maybe this is 0, 0 actually. if you do that, then you will end up with precisely the two dict paths that fit into the squares of, you know, the n by n correctly determined 6 by 6 or whatever this is, 4 by 4, 5 by 5, whatever, with touch points 3, 1. And that's the whole point, that you're summing over pi with touch of pi equaling 3, 1.
Mhm.
Right? And that's exactly what these dict paths are indexing.
Mhm.
Yeah. Yeah. And this is why you actually get d of 3, 1, because it's literally just summing over the dict paths. So let's prove it. How do we do this? So let's suppose k is bigger than 0, and we're going to consider the subset of dict paths that start at 0k and then have an e step, right? So we do k up and then one e step. And then it doesn't make sense for, this is a weird definition when you take k equal to 0, so we're just going to set that to be the empty set. And we're going to define more functions, no surprise. So we're going to define this chi0, and it's basically a way of encoding the corollary. That's basically telling you attach a corner to every, what Eugene was saying, attach a corner, a commutator to every corner, and then assign a north and an east step to the plus and minuses, d plus and d minuses, respectively. Then, so this is, you're going to define this function by precisely saying to every dict path, define a function so that the empty set gives you 1. Whenever you have an e step, you act by a d plus. And whenever you have a corner followed by a bunch of north steps, you're going to add a commutator and then a d minus, right? And notice that I'm not writing in the definition that adding a north step corresponds to precomposing with a d minus. And the reason for that is that this is basically baked into this, right? So this is just literally saying, take our corollary, take the way that corollary was defining chi of pi 0, and just define a new function so that it's defined piecewise in this way, right? Good. So now we have this function, and we're gonna use it to get what we want. So the first step is, let's suppose that alpha is some composition of length L. And we're going to let d alpha basically be all the dict paths whose touch points are indexed by alpha, right? Which is our indexing set inside the shuffle conjecture statement. So, and then I want you to recall that if you take touch prime of pi, the definition of this touch was basically you took a bunch of differences of this ti that was given as the bounds of this dict path, right, where you did a bunch of north steps, east, north, and then whatever, on some other dict path pi 2 that was obtained from the original dict path here, of which you were computing touch prime, right, by doing first L at north steps and then an east step. Why am I reminding you of this? Because the point is that any dict path in this set that has touch points alpha have to look like you first do L north steps and then you do something else. So they all start with L north steps, where L is precisely the length of alpha, right? So this is a characterization that's going to be really useful. Questions? Because I feel like I am just talking and talking quickly at that. No questions. Okay. In that case, well, we're going to use precisely the corollary for chi pi 0, right? Which shouldn't surprise you, which is that you get chi pi 0 by doing all these computations and then doing a d minus to the L. So this basically is just direct from the definition of chi pi 0 and the definition of this chi. So this is pretty straightforward. Good. What is the next step? The next step is we're going to define this n alpha to be the following thing, right? We want to define n alpha to be the sum of t to the bounds, but instead of having a chi pi 0 here, we're going to define these like weird symmetric functions, like essentially the same thing. And we're summing again over the right indexing set, which is dict paths with touch points alpha. And then we're going to notice that since this is true, right, and this chi pi 0 can essentially be substituted for d minus of L of chi 0 of pi tilde, then if you just pull the d L out, then that means that this is just d minus of L applied to n alpha prime, right? Which is just this. So that was part 1 of the theorem that we were trying to prove, which is this. It's basically that d alpha can be obtained from these n alphas. Now what remains to show is that this n alpha prime really truly is defined by these recursive definitions, that it really does satisfy the recursions. Right? So it reduces to showing that n alpha prime, this n alpha prime really does satisfy the recursions. Questions? Do stop me or say something. Okay, good. So what is the third step? So step 3 is, remember that alpha was a weak composition of length L. So we're going to partition it. We're going to separate it into 2 compositions. We're going to label the first R of them by sigma and the last L minus R by beta. And then we're going to define this new function that is going to go from dict paths. It's going to be indexed by sigma and beta. Does someone have a question?
How do you choose R?
Oh, so R is not, it's basically saying pick an R, it'll vary later on.
Okay.
So just some R, there's no choice, yeah. Pick an R, whatever, and then let sigma be the first R and beta be the remaining pieces. And then we're going to define this new function, and it's going to go from dict paths with touch points alpha, right? Alpha beta is really just alpha. Sorry, sigma beta is just alpha. So dict paths with touch points alpha to dict paths whose touch points are now basically the first entry is 1 plus beta. So this is the same as saying the first entry of the touch composition is alpha I for I bigger than R. And then you have alpha 1, alpha 2, all the way to alpha R. All right, so that's the new touch composition. And the way you're going to get this map is you're going to take a dict path here, which remember is precisely characterized by the fact that it starts with as many north steps as the length of the touch composition, right? So the length of this touch composition is L of sigma plus L of beta, which is really L, but I'm just explicitly writing it out. And then we're going to map that to the following dict path, which is, again, notice starting with L of sigma plus 1 north steps, and L of sigma plus 1 is exactly the length of this because it's the length of sigma plus 1 piece, right? One more entry at the beginning. So this ensures that this really does live in this set. And then if you go through and actually check it, you can see that the touch composition of this side is equal to exactly what you want it to be. That's great. And that the bounds of the dict path that you get on this side is equal to the bounds of the path on the other side plus the size of beta, right? Good. Why am I telling you all this? Sorry, this is kind of a long proof. Because what that means is that if you fix a sigma, right? So if you give me a fixed sigma for the first R letters, of length R, and you give me any integer b, and then basically you're allowing yourself to vary beta, right? You take the union over all possible compositions beta of length b. So here b, I'm just saying let b be L minus R, be whatever you want it to be. I'm varying L, I'm varying b, it's the same thing. So pick a sigma and let this vary. Let this vary over any sort of weak composition as long as it has the right length, right? It has however many slots. If you do that and you take the disjoint union over that set, then that is equivalent to saying, all right, let me take all the dict paths of the form n of L of sigma plus 1 like this, right? Where this number here is just, well, B, because that's that number varies because the number of parts don't matter as long as they sum up to B. And then this, the disjoint union of that is precisely this set. Because if you're letting this vary, the only fixed part of this is the fact that it starts with precisely L of sigma plus 1 north steps. So that's the defining feature of being in the set of dict paths with touch points, with touch composition 1 plus beta comma sigma. Okay, that was kind of confusing. So let's take a little moment and maybe internalize this. And why do we need this bijection, right? That's all this is saying. This whole step 4 was just about setting up a bijection between dict paths that live here and dict paths that live here. And here's why, because this is what allows us to prove that n satisfies the required recursions. So let's do b equals 0, right? So if we set b equals 0 here, this is equivalent to saying that the set 1 sigma is equal to, well, if b equals 0, the disjoint union is, there's just one thing, right? Which is basically this. And what that's telling us is that there's a bijection between dict paths that have this touch composition, i.e. that they look like this, and dict paths that live here, i.e. that they look like this, right? They have more north steps and then an east step. What that means is that if we go back then to the definition of n sigma prime, right, which was this, and we basically just substitute all the pi's under this this mapping, under this bijection, right? Then here, the pi becomes the image under this path. Chi 0 of pi basically becomes east of pi because that's exactly what you're doing to the dict path. You're adding an east step. The indexing set then passes from being here to being here, or from being here to being here because we're applying our map gamma, right? So we get that this is equal to this. You use the fact that bounds on this set is actually equal to bounds because beta was 0, so you're adding 0. And then you use the fact by the definition of chi of 0 that adding an e step inside is just equivalent to adding a d plus in front. So you basically just use all these characterizations that you've had all along, and you see that this is really just the same as adding a d plus to n alpha, which is exactly the recursion that we were after, right? That n alpha, adding a 1 at the beginning is the same as adding a d plus to n. So they behave in the same way. And then the more complicated recursion for adding an arbitrary a at the beginning of a composition is more complicated, but it follows the same idea, right? So it really all comes down to precisely this bijection, which is, it took me a while to really understand this. So if it's not totally clear, like it's not meant to be trivial. Like this is not a super obvious statement. Maybe it is to you, but it wasn't to me. And I really sat and thought about it. So yeah.
Can I say something?
Please.
So the way I think about this is completely different, I think.
Great.
Because they phrase it in this way. So there is this bijection between dinf and bounds. So there was this bijection of Haviland and whatever. So on one side, you have dinf statistic, and you have the touch point, which are actually touch point of the dict path of the diagonal, right? On the other hand, like what's happening here is that here you have a bounds and you have this touch prime, which I don't really understand, to be honest, but that's fine. And so like if you go back to that side with dinf and the normal touch points on the diagonal, I think what this lemma is saying is that you look at the first, so you have a dict path, you look at the first point where the dict path touches the diagonal. And then you're saying, well, so you take everything after that, that's again a dict path. And before this, you just have like a step like this, and then you have a dict path of one smaller length. It's like the standard Catalan recursion that you have this one smaller dict path in the middle. and you sum over all possible touch points in this a minus 1 by a minus 1 square, right?
Mm-hmm.
You see what I'm saying?
I
So
think.
basically, like if the first step is equal to a,
Mm-hmm.
so this recursion says that, like, just take this first part. So there should be vertical step in the beginning, horizontal step in the end, and then there should be some dict path in the middle, a minus 1 by a minus 1. And then everything after that is some dict path with the same touch points as the original path.
Mm-hmm. Mm-hmm. Mm-hmm.
And then the point is that if you break it at this point a, the dinf is just additive. So am I saying this right? Is it additive though? No, I don't know. But like there should be some statement. So the statement about bounds, if you scroll up.
Yeah. Wait. Yeah, there it is.
Yeah, this blue statement about bounds, that bounds is this plus this. I think it says that you can compute bounds by like looking at these two paths separate. So the sigma and beta are basically these two parts of the path.
Mm-hmm. 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 Mm-hmm.
And then there should be some statement about dinf, which I might be confused about, but it's
No, there is. I wrote it down, but it wasn't immediately applicable in the proof, so I just didn't write it.
Mhm,
But there is a way of comparing the dinf or the inf, I think.
mhm,
Whatever.
mhm. Yeah, but I think like what's really kind of like the way I understand it is not via bounds, but like really you have the touch points and you have this Catalan recursion and you look at the first touch point
Okay.
and you go from there.
That might be a clear. Yeah, I found this argument honestly very confusing. Like I said, it took me a while to understand it.
But I think that this bijection on this page is literally what I just.
Okay. That's actually very helpful. Thanks, Eugene. Okay. So let me fail at finishing the proof today. God, we're finally getting to the interesting stuff. Okay, so let me continue. So now let's remember that at the beginning I told you that we had these operators, right? These TIs, D pluses, D minuses, D plus stars, whatever. And they're all acting on VK. They're all acting on these bigger spaces. Why is this not working? Oh, there it is. They're all acting on these bigger spaces. And right, and here we're setting V to just be the direct sum of all these spaces because we're going to be dealing with all of them simultaneously. So we're going to define an algebra, and this is just a way of encoding all the information together. We're going to define A to be the algebra that's generated by the TIs, not the TI inverses, just the TIs, and then D plus and D minus, and modulo all these relations. The relations don't matter. They're useful in proving stuff, but for our purposes, they don't matter. Here they are. So they satisfy a bunch of commutation relations. Great, whatever. Okay, and then we're going to recall that we had an action of these operators on these set VIs, right? On the VIs that we just talked about at the beginning, where the TIs were defined by these de Moivre-Lustig operators, and then we had the D plus and the D minus were plethistic operations, right? And then we also had, and this is just because it's going to show up, we also had these operators CR and BR, right, that were defined by Hagelin, Morse, and Zabrocki. And they're, again, these plethistic operators composed, they're basically series. Just think of them as series. That's really what they are. They're series, alternating series of H's and E's with some plethisms showing up. That's exactly what these two things are. Right, and you can define C alpha by basically just instead of R, you act by a composition. And these two things are related by taking Bm and swapping Q's for 1 over Q and composing with the Weyl involution that swaps E's and H's, right, on symmetric functions. So basically, if you know how to write something in terms of B's, you can write it in terms of C's and vice versa by composing by an involution. So this is a relation that will prove useful. And then also I want you to just recall that if you act by D minus, and then you have these multiplication by yi's, that is equivalent to just acting by these operators bi. So just a formula, you can prove it, it's very easy, very straightforward, but I'm just reminding you because we're going to use it shortly. So first theorem of the section here is that the operators, all these plethystic operators, all these definitions give us a representation of this algebra A on our direct sum of vector spaces. Okay, how do you prove that? It's really straightforward. You basically just check that these definitions, all these plethystic definitions, these operators here, satisfy all these relations. So it's really a very straightforward proof of just proving that you actually have a well-defined action. Not too exciting. And the second thing, which is a lot more useful, is that if you consider PK to be basically the projection onto from V onto the kth VK, right? The kth VK onto VK. So you can think of this, if you're familiar with idempotence, it's really just an idempotent onto VK. Then you can think of the operators of A, right, as acting on V and then projecting with VK. You get a family of elements that live, and then projecting to V0, you get a family of elements that live on V0. That is just a vector space if you just take the span of all these images, right? And if you consider a map from this vector space to V, then the statement is that this is an isomorphism of representations, right? So for those of you who might not be super familiar with representation theory, let me just remind you that all this statement is saying is that if you think of this as a vector space, which, like I said, all you're doing is saying, let me take V, right, my direct sum of vector spaces, VK, I'm acting on them by all these operators, right? And then you get whatever you're getting. And then you project down onto V0. So you basically just say, let me project all these operators down onto symmetric functions and forget all the y's. You take a bunch of elements that are really just symmetric functions. You're going to take the span of these things. You get a vector space. That is what AP0 is. So that is isomorphic to V. That's part one of as a vector space, right? Just a vector space isomorphism. That's the first part of the theorem. So it's an isomorphism that sends 1 to 1. This is just like 1 in symmetric functions. And the second part, that it's an isomorphism of representations, is basically just telling you that this as a vector space has an action of A by these plethystic operators that we just talked about. This also has an action of A because you can just, it's a bunch of symmetric functions, so obviously you can define the same action, A acts on it. And the statement is that those actions, the action on this side and the action on this side, commute through this isomorphism of vector spaces. Basically, you can act here and then go under the isomorphism, or first go under the isomorphism and then act, and you get the same thing. So that's all this is saying, that the structure is basically the same on both sides, right? And under this isomorphism of representations, if you then take this vector space, the elements of this vector space, and you hit them with a projection onto the kth level, let's say, then you actually just get precisely the kth level. So it behaves nicely. That's all this is saying, that really all the information that you want about V is already encoded in the algebra itself, right? That's the whole point of this, that really the vector space, all the elements in this vector space, all the symmetric functions, everything you want to know about symmetric functions, the algebra by itself already knows. You don't need the vector space really, because it's completely isomorphic. Right, and remember that the point of this story is to translate everything, all the symmetric functions and all the operators, to the language of the D plus and D minus and YI operators. So that's part of the story. So let me.
Can I interrupt with a comment?
Please.
So I like to think of these PKs as idempotents that actually live in the algebra A, because if you look at the definition of D plus D minus and how they act, you need to know which VK you're in.
That's exactly, yeah. That's how they're actually defined. I didn't do that because I thought thinking about projections might be easier for people that are not familiar with idempotence. But yes, of course. Yes, thanks, Monica. That's exactly how they define it. Yeah.
I would also add that, so the meaning of the theorem is that you start from 1 in V0, and then you can go arbitrary up and down, and then you end in V key. And then the claim is that any such operator you can actually rewrite in terms of just going up by d plus to 1 in vk, and then applying some operator there, basically. And so every vector, in particular, every vector in vk you can get this way, and all operators from v0 to vk you can obtain this way.
Mm-hmm. Mm-hmm.
So it's
Yeah.
some kind of PBW thing, right?
Yeah. Thanks. Okay, so let me basically tell you, how do you prove this? Well, proving that it's a representation, you just prove that the relations are satisfied. That's easy. To prove that you actually get an isomorphism of, to prove that this space is isomorphic to this space as a vector space, you need to show that, remember that the V's have Y's, right? Where are you getting the Y's from? Like how are the Y's showing up out of these operators? So you basically prove that you can generate the yi's by just acting by a commutator of d plus and d minus, and then composing with ti's. So basically the y's multiplication by yi in vk is encoded by acting by these operators d plus, d minus, and ti's. So you have all the information already, right? You can generate everything. Right, so
What is f here?
f is any function in vk.
Okay.
Anything, yeah. And so, oh yeah, sorry, I should have said this is really yi on f. Thank you. Yeah. So multiplication by the variable yk is equivalent to acting by the composition of these operators. Good. So proving this is easy. Proving this again is easy because you just define them this way and then prove that this equation really does give you multiplication by yk. And the reason for that is that, remember that d plus and d minus were plethisms that had yk baked into the definition of the plethism. So that's why the yk shows up. Okay, so this is easy, just a straightforward computation. Proving that that this is a legit isomorphism, though, is a bit more interesting. So the next thing is you want to prove that this set, this set, whatever, some functions that you're getting here, actually give you a basis for your vector space AP0, and that they're mapped to a basis of V. So I'm going to prove this, and then I'll be done. Sorry that I'm going a little bit over, but this is a cool proof. Jose, did you have a question? Oh, okay. So all I'm saying here is, if you start with P0, so you're projecting onto P0 onto V0, so these are really just symmetric functions. Right? You're going to act by d plus k plus m times. You're going to act by y1 through yk plus m, so your variables, to some powers, and then you're going to bring it down. So this d minus m ensures that you're falling back into the right level. And the condition is that that ak plus 1 through ak plus m, so the last m a powers, are basically a partition. That's this condition. So how do we do this? So step 1 is to show that this this set here, if we don't put any conditions on the a's, really is a spanning set. So remember, right, that what is AP0? AP0 is take your operators d plus, d minus, ti, act, and then project. So if you have a spanning set for this vector space, that means that if you act on this set, right, on these elements by d plus, d minus, and ti, the result also has to be expressible over things of this form. So that's equivalent to saying that this set is invariant under the action of ti, d plus, and d minus. And that's exactly what they show, right? So they basically take an object of this form, apply d plus, apply d minus, and apply ti, and show that the result can be written as something, as a sum over stuff of this form. Right, and at this point, we don't have any conditions on the AS. They're just whatever they want to be. This is not hard. It's tedious, but it's not hard. It's just you compute it, and then you use all these commutation relations between the TIs, the D minuses, and the slew of relations that you have to get it. But it's very straightforward. Good. So that shows that this spans this vector space. The second step is to show that you really want those relations on those set, right? Because at this point the set is too big, so we want to cut it down. So the second step is to show that if you take this these objects, right, these symmetric functions, and you basically permute the things around, right? Again, use the commutation relations to flip things around, then you can always express this where the AIs have no relations as a sum over stuff that is 0 when restricted to V0, and one term, only one term that looks like this, right, which is essentially the same thing, but where the conditions are satisfied. So if you take something of this form with no conditions on the A's and you apply a bunch of relations, then you can rewrite it as a bunch of stuff that's 0 on V0 and one term where these relations have to hold. So equivalent, that basically shows you that you can restrict this spanning set to a spanning set where the elements have to satisfy these relations. Does that make sense? Good. Again, this is very straightforward to prove. You just write it out and play with relations and show, hey, this is 0, whatever. Not very enlightening. The cool part is how they prove linear independence of the spanning set. So what they do is they take this spanning set and they map it to a basis for your vector space under this isomorphism, right? And because they're taking a spanning set and they're mapping it to a basis, that proves that that set is also linearly independent, which means that it is a basis for the original space. So how do they do this? So this is where we're keeping track of, well, of where the V's live. So we start with our spanning set, right? And here we are assuming that the last M A's are a partition. So we take this, we applied it to 1. And the first step, we notice that this one lives in V0. And if we apply D plus K plus M times, we still get 1. But now that 1 lives in VK plus M, right? We're using this relation. Then we're going to use, I didn't tell you this, but there's a whole slew of relations between the yi's and all these operators as well. So in particular, the yi commutes with the D minus. So that means that I can take this D minus and basically slide it wherever I want. And I'm not going to slide it all the way to the end. I'm going to slide it past the first k y's, and then I'm going to interpolate it with the remaining yi. So I'm going to do a D minus, right? Let me take this. There's M of them. I'm going to slide it past the first k. And then for the last m y's, I'm going to do a D minus and then a y, a D minus and then a y, or a power of y, and so on. The reason I'm going to do that weird distribution is because I want to recall that if I do a D minus and then a yk, that is equivalent to acting by this BI operator of Hagelin-Morse-Abraki, right? So here you're basically going to substitute that for this. You're going to substitute, this D minus yi for that, and so on. So here you have a composition of precisely MBBs, right? With some minus signs that are popping out. And the first y's stay the same. And this is where that condition that these letters were a partition matters, because this object, right, if we just ignore the y's for a second, this symmetric function here, this composition of stuff is a symmetric function because they are literally generators for Hall-Littlewoods or modified Hall-Littlewoods. That's the whole point of the Hagelin-Morse-Abraki construction, is that these B's are essentially variations of what are known as Jing operators. So they generate Hall-Littlewood polynomials, right? Hall-Littlewood polynomials are not only symmetric functions, they are a basis for the ring of symmetric functions over QQ or QT, whatever, some extra parameter, which is fantastic because, well, that immediately gives us that these elements are precisely a basis for this space, right? Because we have a basis for symmetric functions that comes from these literally being Hall-Littlewood polynomials. And then this is just a monomial in Y's, any monomial, because we have no conditions on the first, on A1 through AK, right? We only have conditions on AK plus 1 through AK plus M. So the fact that these are free means you're just taking a Hollywood, multiplying it by whatever monomial in Y's you want. That's exactly a basis for the VKs. And so that proves that this generating set here that we had for AP0 really is mapping under this isomorphism to a super nice basis for symmetric functions or for VKs, right? So it's linearly independent and it spans and it's exactly what we want. And then basically once you have that in hand, then you get exactly the content of this isomorphism. You get that one maps to one and that things behave really nicely, right? That the kth level really is basically, as Eugene was saying, constructed or obtained by starting with 1 in V0, just 1 like in symmetric function land, applying whatever operators you need to get to level K, doing whatever operations you want up there, and then basically bringing it back down to V0. So any operation you want to do on symmetric functions really, really completely is equivalent to working in this much bigger world where you have a lot more freedom and a lot more structure or more power, and then reducing it back. So that's why this thing that seems a little bit weird, this theorem, is actually super powerful and really cool. I'm going to stop because we're over time. And I'm so sorry, Eugene. I'm going to take your time next week to finish. I'm so sorry, everyone.
Absolutely, no problem.
Long.
No problem. I have one comment though. So here, like you said that D minus commutes with Y's, it commutes with almost all Y's, but not the last one.
Oh,
So
it does not commute with YK?
It doesn't commute, like in this case, with YK plus M, because you are in VK plus M, right?
Okay.
So this means that you can take D minus, you can push it all the way through, but you can't push it through. I mean, if it would commute with the last one, you would get D minus of 1, and then that would be stupid, actually.
Yeah, that's true. You're right. You're right.
But you push it
Yeah,
all the way until you can push, right?
Sorry, can I just make a comment?
Yeah.
Like, if you say that you live like in VK, then D minus YK makes sense, but YK D minus doesn't. Because if you apply D minus and then you go to VK minus 1, there is no YK there. There is some relation I don't remember, but yeah, one needs to be careful.
Right, but like in this formula, so it's not like a weird thing to do. It's really like the only thing you can do. So you can push all D minus all the way until it hits the last variable and stops. And then you take the next D minus and like push it to the right until it hits the last variable, which is now K plus M minus 1, and stops there. And then you kind of push it all the way to the right until you can do it.
Okay. That's a good point. I didn't realize this condition. And so I was just like, oh, they just distribute it this way because they're smart. But I guess you distribute it this way because you have to. I mean, they're still very smart. So that doesn't negate that. Cool. Thanks, Eugene. And Jose. Cool. Does anyone have any questions? Sorry. I feel like today we covered a lot and it was hard, a lot of it. So questions, comments, discussion. I don't have any exercises. I'm sorry. All right. Thanks. Yeah, we can sit and chat if you guys have any comments or questions. I'm going to stop the recording though, because I feel like we have nothing more to say.